Okay, so let's talk about the fourth and final colligative property, which is osmotic pressure. So, what is osmosis? Let's talk about osmosis first. And osmosis is basically the selective passage of solvent molecules through a porous membrane from a solution which is more dilute to a solution which is more concentrated. So that's what is being demonstrated in this diagram right here. So here we have two compartments, two vessels, let's say, separated by a semi-permeable membrane, which, by the way, is basically a membrane. Let me just show the definition here. It allows the passage of the smaller solvent molecules, but does not allow for the larger solute molecules to pass through. So, for example, let's say the solution is a solution of glucose, right? Glucose is larger in size, water is a smaller molecule. So therefore, the semi-permeable membrane has very small pores, which allows only the smaller molecules to pass through and does not allow for the larger glucose molecules to pass through it, all right? So as we stated before, osmosis is where you have the solvent molecules passing through the membrane from the more dilute solution over here on the left to the more concentrated solution on the right, all right? And that will continue until both solutions reaches a situation where they're both isotonic, which basically means that they have the same concentration. We're going to see that term again in a slide upcoming shortly. So as a result, both solutions will have what we call different osmotic pressures, which is represented by the difference in the height of the two liquids in this diagram right here, all right? And the osmotic pressure is, by definition, the pressure required to stop osmosis, right? So that's basically what is going on as far as osmosis, osmotic pressure, and semi-permeable membranes are concerned. Okay, so this is just another representation. Not quite accurate because there's no semi-permeable membrane, but this underscores the importance of understanding what is happening in osmosis. Basically, you have the transfer of solvent molecules from the more dilute solution to the more concentrated solution, all right? So let me just skip all this here, because I want to get to this right here. This is the formula that we use to calculate the osmotic pressure. The osmotic pressure is represented by the Greek letter pi, right? And that is equal to mRT, uppercase M, RT. M is the molarity of the solution, R is the molar gas constant, and T is the temperature in Kelvin. And this should look familiar to you if you remember when you encountered the gas laws in General Chemistry 1 or Introductory Chemistry. It's basically the same equation. The only difference is that we replace we replace P with pi to get this equation right here. As far as R is concerned, depending on the units that you're dealing with, in this particular case, however, I would say that R must be equal to, write it here, R is equal to 0.0821 liters atmospheres over mole Kelvin. All right, so that's what R is. If you use that value for R, then basically P would be in units of atmospheres, right? We know what the units of molarity is already, and we know what the units of temperature is, which is Kelvin, all right? So that's basically as far as this equation is concerned. All right, now the whole process of osmosis is very important, especially when it comes to biological systems. For example, when a patient goes into a hospital and needed to be infused with electrolytes, the concentration of the electrolytes have to be carefully designed whenever they're let's talk about these different terms. Now here we have a red blood cell, right? A red blood cell is basically a tissue which inside of it has different proteins and ionic components and so on. All right. So inside the red blood cell, you have a certain concentration. Now, if that red blood cell, and let me just say that the tissue is semi-permeable, right? So you're going to see how osmosis works in this particular situation. Now, if you take that red blood cell and place it in what we call an isotonic solution, where the environment of the solution, its concentration is the same as that of inside the cell, then basically that solution will not have any effect on the cell because basically you won't have any net transfer of water going outside from inside the cell and vice versa. Now, in the case where the solution surrounding it is more concentrated, we say that that solution is hypertonic. And what that means, I'm sorry, I misspoke. When the solution around the cell is less concentrated or more dilute, that solution is hypotonic, all right? And what that means, or the result of that, would be that the solvent molecules, the net transfer would be from outside the cell to inside the cell. The result of that is that the cell will swell up and burst. The medical term for that is crenation, or I should say hemolysis. And that is something, of course, which is not desirable when it comes to taking care of patients in this way. And then we have the opposite, where the solution is more concentrated, which means that the net movement of water molecules would be from the inside to the outside of the cell, and therefore the cell will shrivel up, and that is called crenation. Again, that is not desirable. What is desirable is the isotonic situation where the concentrations of the particles outside the cell is equal to that inside the cell. All right, so this is just one example of osmosis being important when it comes to biological systems, and there are many others which I won't be able to get into at this time. Okay, so what I'm going to do is stop here, and the next video I'm going to post will dealing with well, tell you what, let me continue with this first. So in the case of non-electrolyte solutions, these are the four colligative properties that we discussed, right? We talked about the vapor pressure lowering, the boiling point elevation, the freezing point depression, and osmotic pressure, right? Now, the assumption that we're dealing with in all these cases that the particles, the solute particles, do not dissociate, right? So, for example, if we're dealing with a solution of, let's say, glucose molecules, the glucose molecules, when they dissolve, they don't break up into smaller fragments, all right? Now, what we're going to see in the next video is where you have a situation where the solute will actually dissociate, for example, electrolytic solutions, and we're going to see the effect that that has on the colligative properties of such solutions, all right? Okay, so until next time.